Ever wondered how scientists decode the microscopic world of kidney tissue? It's not just about spotting structures, it's about understanding their exact shapes, sizes, and relationships. Today, we're exploring DyMorph-B2I, a revolutionary tool reshaping how researchers analyze kidney diseases at the cellular level. Let's start with a challenge. Traditional methods rely on binary masks, black and white maps that label every pixel as part of a structure. But here's the problem. These masks can't distinguish individual structures. Imagine trying to count apples in a basket, where all the apples are a single red blob. You'd miss overlaps, tiny details, and end up with inaccurate counts. In kidney tissue, where structures like glomeruli, tiny blood filters, or tubules, tiny tubes, are tightly packed, this leads to errors. Old techniques like watershed, which splits images like a landscape into regions, or skeletonization, which reduces shapes to their core lines, struggle with the kidney's complexity. It's like trying to untangle a knot with scissors. Sometimes you cut what you shouldn't. Enter DyMorph-B2I. This isn't just another tool. It's a smart, adaptive system that combines classical image processing with modern tweaks. Think of it as a toolbox where each tool, watershed, skeletonization, morphology works together, but with a twist. It learns from the image itself. Here's the breakdown. First, the system uses watershed to roughly separate structures, like peeling apart tangled wires. Then, skeletonization highlights the core of elongated structures, like tracing a snake's backbone. Finally, morphology operations. Think of them as erasers and expanders, fine-tune edges. But here's the magic. DyMorph-B2I dynamically adjusts parameters, like zooming in or out, based on the shapes it sees. It's like having a personal assistant that tweaks tools in real time for perfect results. The numbers speak for themselves. In tests, DyMorph-B2I outperformed older methods. For example, it detected 20 distinct structures in a single image, while traditional methods missed several. Why does this matter? Accurate counts and measurements are critical for diagnosing kidney diseases or tracking treatment effects. What makes this approach revolutionary? Its flexibility. DyMorph-B2I can be customized for different kidney structures and is open source, letting researchers worldwide build on it. Imagine a future where automated tools help doctors spot early disease signs or test therapies with precision we've never seen. Now, let's dive into the metrics that prove its success. Scientists use two key measures. MAPE PE mean absolute percentage error, and PE percentage error. MAPE PE acts like a scorecard for accuracy. Lower numbers mean results closer to human experts. But MAPE PE alone isn't enough. PE tells you how wrong a method is. Positive values mean over-segmentation, splitting things into too many pieces, while negative values mean under-segmentation, missing parts. Together, they reveal a method's strengths and biases. Testing revealed DyMorph-B2I's edge. Traditional methods like watershed or morphology often over-segmented, while skeletonization was inconsistent. Even simple combinations of techniques introduced new errors. But DyMorph-B2I, it adapted in real time, avoiding one-size-fits-all pitfalls. For tricky structures like PTC, tiny, hard-to-detect kidney components, it delivered results that matched human experts. In densely packed areas like tuft or art, it adjusted parameters dynamically, avoiding the mess of rigid approaches. The secret: dynamic hyperparameter tuning. Think of it as fine-tuning a guitar. Each adjustment is tailored to the tissue's shape. Without it, methods either split things into too many pieces or miss critical details. With it, DyMorph-B2I creates cleaner, more accurate segmentations even in the most complex cases. So why does this matter? Accurate segmentation isn't just about numbers. It's about better diagnosis, deeper disease insights, and more reliable research. DyMorph-B2I isn't just a tool. It's a leap towards smarter, more precise medical imaging. As research advances, tools like OmniSeg and Segment Anything Model, SAM, are pushing boundaries, adapting to cross-species data and noisy labels. Open-source platforms like PySpatial and Spatial Pathomics Toolkit are accelerating discoveries, while frameworks like CASC-AI tackle challenges like intratumoral heterogeneity. The future is clear. AI is transforming how we decode the human body. From kidney tissues to cancerous tumors, these innovations are turning complexity into clarity. Stay curious, and let's keep exploring how science turns the microscopic into the monumental.